Greetings, students. Today, on the 8th of July of 2023, Professor Penn, who is a very brilliant, high educated person, posted a video on YouTube in which he evaluated the value of a nice series related to Riemann zeta function. And he also derived the value of these infinite series, this closed form expression, as a lemma on the side. And I was wondering why he derived it for all the integers, though he only used the series for natural numbers, and mean that this was the actual series that he needed in his calculation. And though the method that he used was quite simple and quite fast, I just know of another method to evaluate this series that I would like to share with you. And that's by writing the Fourier cosine series of the function cosine of tx, where t is assumed to be not an integer, over the half interval 0 to pi. So we're taking L, which is half the period, as pi. And we know that we can write the Fourier cosine series of a function f of x as a naught over 2 plus the infinite series as n runs from 1 to infinity of a n's times cosine of n pi x over L, where since L is equal to pi, that simplifies to just cosine of nx. And we can find a naught and a n using the formulas that you're most likely familiar with. A naught is 2 over L, so we get 2 over pi times the integral from 0 to L, which is 0 to pi of cosine of tx dx. And this is a quite simple integral to evaluate, and we just get 2 over pi t times sine of tx evaluated from 0 to pi. At the lower bound, we get 0, and at the upper bound, or pi, we get 2 over pi t times sine of pi t, which is not equal to 0 since t is not an integer. And then for an, we get 2 over pi times the integral from 0 to pi of cosine of tx times cosine of nx dx. And using sum and difference formula for those trig identities, we can write the product of those two cosine functions as half of cosine of the sum of the two angles, so n plus t times x plus cosine of the difference of the angles, and then integrated with respect to x. So these twos right here cancel out, and we get 1 over pi times 1 over n plus t times sine of n plus t x evaluated from 0 to pi plus 1 over n minus t sine of n minus t x also evaluated from 0 to pi. Again, at the lower bound or 0, we get 0, and at the upper bounds, we get sine of, so I have that factor of 1 over pi. Not sure why I missed it. So we get 1 over pi times sine of n plus t pi over n plus t plus sine of n minus t pi over n minus t. And if you use the expansion formula for sine of the sum and difference of two angles, from this expression we get sine n pi cos t pi, which is 0, and then cos n pi sine pi t, which is -1 to the n times sine of pi t. And this also similarly evaluates to -1 to the n times sine of pi t. So we can factor -1 to the n sine pi t out of these two terms, and we get -1 to the n times sine of pi t divided by pi multiplied by 1 over n plus t minus 1 over n minus t. And we can get a common denominator here simply as n squared minus t squared. And then at the top, we get n minus t minus n minus t, which is -2t. So finally, for our ANs, we get -2 times -1 to the n times t times sine of pi t over pi times 1 over n squared minus t squared. And this is the expression that we found for A naught. I'm just going to paste it here to be in front of our eyes. And now we're ready to write the Fourier cosine series of cosine of tx, which is A naught over 2 or 1 over pi t sine of pi t. And then we have minus 2t sine of pi t divided by pi multiplied by the infinite series as n runs from 1 to infinity of -1 to the n over n squared minus t squared times cosine of nx. And this Fourier series at x equal pi converges to cosine of pi t. And from the right hand side, we get everything the same except that x must be changed to pi. So we get a cosine of n pi there, which is -1 to the n, and it makes a 1 with this other factor of -1 to the n. So finally, for cosine of pi t, we get 1 over pi t sine pi t minus 2t sine pi t over pi. And this just becomes 1 over n squared minus t squared. Okay, cool. And now since we have pi t kind of all over the place, I'm gonna substitute that with variable z, and this also means that t should be replaced by z over pi. So on the left we get just cosine of z, on the right we have sine z over z minus, there's a 2 over pi, there's a t which is z over pi, and then sine of z times the series as n runs from 1 to infinity of 1 over n squared minus z over pi squared. And now if I divide both sides by sine of z, on the left we get cotangent of z, and on the right we get 1 over z minus 2z over pi squared times the series and running from 1 to infinity of 1 over n squared minus z over pi squared. And to get the closed form expression for our desired sum, which is that thing right there, we need to set a squared equal to negative z over pi squared or negative z squared over pi squared, which means that z squared should be negative a squared pi squared, which means that z could be I a pi. Okay. So on the left, if we set z equal to I a pi, we get cotangent of I a pi, which is cosine of I a pi divided by sine of I a pi, where cosine of I a pi is cos of a pi, And sine of I a pi is I times sinh of a pi. And we can write this as negative I times cos divided by sinh, which is hyperbolic cotangent of a pi. Okay, cool. And now on the left, we get negative I cotangent hyperbolic of a pi equals to 1 over I a pi, since z is I a pi, minus 2I a pi divided by pi squared times the series as n runs from 1 to infinity of 1 over n squared plus a squared. We can write this 1 over I as negative I. So I'm going to change this expression to negative I divided by a pi. And now I'm going to divide out a factor of negative I. So this goes away. This turns into 1. This turns into plus sign. And that I also goes away. And we can also cancel a factor of pi. So we get cotangent hyperbolic of a pi equals to 1 over a pi plus 2a divided by pi times the series and running from 1 to infinity of 1 over n squared plus a squared. And if we solve this for our desired sum, which is the sum of the terms n running from 1 to infinity of 1 over n squared plus a squared, we have to subtract 1 over a pi from both sides and then multiply both sides by pi divided by 2a. So we get pi over 2a times cotangent hyperbolic of a pi minus 1 over a pi. And if we get the common denominator inside brackets, we get a pi cotangent hyperbolic of a pi minus 1. And we can cancel this pi with this pi down there. So now in the denominator, we have 2a squared. And at the top, we have a pi cotangent hyperbolic of a pi minus 1. And let me just verify this beautiful result using my favorite math software, which is Mathematica, aka Wolfram Alpha. And this really looks nice. Can have the sum as n runs from 1 up to infinity of 1 over n squared plus a squared. Let's compare these answers. Yep, a pi hyperbolic cotangent of a pi minus 1 all over 2a squared, and that's perfect. We can also use this to find the solution to Basel problem. Besides the exact value of so many series which can be put into this family. But to get the value of the sum as n runs from 1 to infinity of 1 over n squared, which is the famous well-known Basel problem, we need to take the limit of this expression as a approaches 0, and I just want to recover that pi squared over 6 for some fun maybe. So a pi cotangent hyperbolic of a pi minus 1 over 2a squared. And honestly, I would not like to apply L'Hopital to this twice. So I'm just going to ask Mathematica for the Taylor series expansion